Hello, this is Optics Lecture 2.2, which is on flat mirror images. If we were live in class, I'd be doing this lecture probably the same day as the last lecture. And the essential question is, how do mirrors create image? This is a really important skills lecture. You're going to be learning about something called a ray diagram or ray tracing that you'll be using through the whole unit. So this is an important one. So mirrors are really an incredible human invention. They are a source of fascination for people from a very young age. This is a picture of my son kind of discovering himself in the mirror and really enjoying seeing how the world sees you. What you're looking at in a mirror is an image, though. We've talked about that a couple videos ago. And so the question is, now that we understand images a little bit better, can we classify this image based on our observations, and can we figure out how the image arises from the mirror? So the first question is it upright or inverted? Obviously, it's upright based on the fact that, your head's up and your feet are down. The magnification of this image, hopefully when you look in a flat mirror, you realize you're about the right size. That Oscar in the mirror is about the same size as the real Oscar, so magnification close to 1. And if you remember the difference between a real and a virtual image, you'll recall that a real image is one that you could go to that location of the image and capture it on a screen or a piece of paper. So that picture of Oscar appears to be somewhere behind the wall in my bathroom. Obviously, you can't go back there with a screen and capture it, so this would be a virtual image. So let's see if we can back up our predictions about this kind of image with some real science. So the process of ray tracing is the process that scientists or physicists use to determine what kind of images is created with any optical device. So lenses, mirrors, all the ones we're going to be doing in this unit, and also for determining where the image is going to be located. It's really useful, important skill. So let's take this first example of an object located in front of a flat mirror, sometimes called a plane mirror. And we're going to start by assuming that that object is either generating its own photon, so it's a light bulb or something that's creating light, or that it's experiencing that diffuse reflection. So the light is coming in from some outside source, hitting that object, and it's actually reflecting off in all directions. You'll notice that every part of that object is reflecting light in all directions. So I've got green light rays leaving the stalk of that carrot, and I've got orange light rays leaving the tip of the carrot, but there would be light rays leaving every other part of the carrot as well. Those are real light rays. They actually exist in space, and if you had an eye in the location around the object, you'd be able to see where that object is based on the triangulation of those light rays. But to see what's going to happen using the mirror, the image that's created in the mirror, the first step is to choose any two light rays from one part of the object that are going to be hitting the mirror. So you'll note that there's an infinite number of possible light rays to choose from, and there's actually an infinite number of them that will be hitting the mirror, all the ones that are kind of going to the right on your screen. But I just want to pick two, and the reason you only need two is because you only need two lines to triangulate to a location. They're all going to triangulate back to the same spot, so let's just simplify things and pick two of them. So pick those two, and then you're going to be using the law of reflection to determine where those rays go after they hit the mirror, because it's the reflected rays that are going to be generating the image, not the original rays that are leaving the object. So I drew my normal lines in there, and then drew some reflections. And so now you can imagine if you had an eye at each location where those objects would hit, right? Where would your brain, where those reflected rays would hit, where would your brain think those light rays came from? Well, if you follow those light rays back, they appear to originate at a location back here behind the mirror, that little spot. That spot appears to be the source of the light rays. We know they didn't actually start there. They started here at the carrot. But your brain isn't smart enough to understand that. Your brain thinks light travels in a straight line, so your brain is going to think that the stem of that carrot exists behind the mirror somewhere. You're then, of course, going to just repeat this process for the tip of the carrot, and your brain would take two light rays that hit the mirror from the tip, use that law of reflection to bounce those things off, and then go backwards and triangulate the location of the tip of that carrot. Of course, we could do this for every location in the entire carrot, but if you know where the top of the carrot is, you know where the bottom of the carrot is, you can make the assumption that the carrot fills in the space in between. So at this point, you've located the image of the carrot. It's located there behind the mirror, just like we would expect with our plane image. And we'll talk about classifying that image in just a second. But this process is super important, and we're going to be doing the same generic process for every optical device in this unit, so make sure that you sort of highlighted this in your notes and review this page frequently. Okay, so now that we've got our image created, how do we classify that image based on our ray tracing diagram? Well, of course, you can see very clearly whether the image is upright or inverted. We've got the top of the caret at the top, the bottom at the bottom, so we've confirmed that it is going to be an upright image. Magnification, there's actually two ways to calculate magnification, or M. Magnification is defined as the ratio of the height of the image divided by the height of the object, or the distance to the image divided by the distance to the object. For some reason in this equation, distance is represented by the letter S. If you took AP Physics 1, you might be familiar with that, but in any case, the S stands for distance, the H stands for height, and the subscripts tell you whether we're talking about the object or the image. This is the first equation from your equation sheet, your AP Physics 2 equation sheet that you'll discover in the coming year. And it basically says that the absolute value of magnification is equal to I over ho or SI over SO. So you can use either of those ratios to define magnification. It's probably more common to use the distances because it's easier to measure those distances based on your ray tracing diagram than it is to measure the height of the object. You're less likely to mess up on those, and so usually you'll use the distances. As far as units go, it doesn't matter what your units are because so long as you are consistent, whatever you measure the height of the object in, if you use the same units for the image, the units are going to cancel out. Magnification is a dimensionless value, which means it's just a number. It doesn't have any units because no matter what units you use, they cancel out in that equation. So in this case, and for all plane mirrors, the image is actually the same distance away from the mirror as the object is, and you could prove this with a geometrical proof if you wanted to. So the magnification of objects in plane mirrors is equal to 1. The last classification is whether this is a real image or a virtual image. And the way you decide that is whether the real light rays actually intersected in a single point, or whether it is virtual light rays or kind of imaginary light rays that are intersecting. In this case, those light rays didn't actually exist at the location of the image. So those are virtual light rays behind the mirror. My brain thinks that's where the light came from, but the light didn't actually pass through that point where the image is located. So that tells me that this is going to be a virtual image, just like we sort of predicted about this plane mirror. Okay, that's it for this lecture. Take a few minutes and revisit the essential question, which is how do mirrors create images? And then please click into the practice assignment for this and do a little bit of ray tracing for plane mirrors and practice to check your understanding. Thanks for watching.